important problem from group theory, and the problem is a circle be a semigroup and xy belongs to S, any two element of S, that is the semigroup, and it is given that for x and y, x square composition y, this is equal to y, and it is also equal to y composition x square. It is hold always for all value of xy. We have to show that a circle is a abelian group. Okay, and we first see what is group, that is the definition of group. To form a non-empty subset together with a binary composition, here it is given that the circle forms a group if four properties are satisfied. Okay, first one is closure, second one is associative, third is identity, and fourth is inverse. And together with them, if this property, that is the fifth property, and this property is abelian property or commutative property, for all AB belongs to G, imply A composition B, this is equal to B composition A. Okay, in this case, this group is said to be commutative group or abelian group. And if only first two property are hold for the algebraic structure S circle, then we say that this algebraic structure is a semigroup. Okay, so in our problem it is given that it is a semigroup. So to prove this semigroup becomes a group, we have to prove these two properties, that is it has the identity property and it has the inverse property. Okay, and together with them also we have to prove this is abelian property hold. Okay, now to prove one by one, we first try to prove identity property, and we know that in a group identity element always unique, that is only one identity element exists in a group, right? To prove identity property, it is clear that from the given condition here x square here work like an identity element, because if we take this is E, generally identity element is written as E, so E composition Y and Y composition E, this is becomes Y for all Y belongs to S. Okay, so it is clear that x square works like an identity property. So we have only proved that this identity property is unique or identity element is unique. To show identity element is unique, we write this relation for two elements. Let P and Q be two elements of S. Here it is given that the set is S. Okay, and another element A also, let this is also belongs to S. Then we write this property as P square composition A, this is equal to A, and also this is A composition P square by using P and A. Similarly, by using Q and A, we get Q square composition A, this is equal to A, this is equal to A composition Q square. Using this property, we write these two lines. Okay, and since Q belongs to S, P belongs to S, and since it is a semigroup, so closure property already hold in it. So we use the closure property, we may write Q composition Q, this is Q square, belongs to S. Also P composition P, this is P square, it is also belongs to S. Now we put Q square in place of A in the first relation, and we put P square in place of A in the second relation, and we get two relations which are given by P square composition Q square, this is equal to Q square, this is equal to Q square composition P square. And from the second line we get Q square composition P square, this is equal to P square, this is equal to P square composition Q square. and it is clear that this right side, this is equal to left side, and also this right side is also this left side. So this and this are equal, and this are equal. So these two terms must be equal. So we can write this p square, this is equal to q square. And we see here this identity element is unique because p square and q square are same. So we say that p square, this is equal to q square, and we write it, this is e. Okay, and being identity of S circle. Okay, so we write, so we can say for all x belongs to S, we get x square, this is equal to e, being identity of S circle. Okay, so identity property hold, that is third property hold. And now for all x belongs to S, we get x square, this is equal to e, and from here we write that x, this is equal to x inverse, that is every element is inverse of itself. Okay, so here we say that inverse property also hold. Inverse of every element exists in a circle. Okay, so we say that a circle is a group. So we first prove a circle is a group. Now we have to show that this is abelian. To prove abelian, we take two elements. Let A and B belongs to S, and we get a relation x equal to x inverse for all x belongs to S. So we write A, this is equal to A inverse, and B, this is equal to B inverse, because A and B both the element of S. Now A and B both the element of S, so by closure property we may write A composition B must be belongs to S, and since A composition B must be belongs to S, so we get A composition B, this is equal to A composition B whole inverse because of this property, right? Because every element is inverse of itself in the group. Now we know that the formula of A composition B whole inverse, this is equal to B inverse composition A inverse in a group, and we write again B inverse, this is equal to B, and A inverse, this is equal to A because of this and this. So we write this is B composition A, and we get that A composition B, this is equal to B composition A for all A and B belongs to S. So we say that the group becomes commutative or abelian group, right? Very simple proof, but interesting problem of group theory. Thank you for watching.